Okay, great. Thanks, Tony. Sorry about the delay. We were technical problems for the last seminar of our series. Tony needs no introduction here, so you can begin, Tony. Thanks very much.
Thank you very much, and thank you for having the honor to be the last before the break. So I propose to talk about Pirogov-Sinai theory, and it's actually maybe 5 years ago I gave a series of lectures on this topic at Dias from the book by Sinai. And already at the time, I wasn't quite happy. There were details of his outline that I didn't fully understand. So I wanted to, study that in more detail. And I thought maybe because it's not clear in places, I should write it up. And then during the lockdown, I thought this is a good opportunity to do that. And so when I started writing it up, then I discovered that in fact, it is worse than I thought, because there's a whole piece of the theory missing. And it seems that, so his book is actually based on 2 articles by Pirogov and Sinai. And it turns out that actually at the time, the theory was not finished. And then there was another student of Sinai's who apparently finished it, but I looked at the articles, and in the typical Russian way at the time, they must have discussed it all among each other, and the actual article is only 3 pages long, and it's not clear what they do. So I had to basically finish the theory myself. And so now, the theory itself is extremely complicated, and it's obvious that I cannot go into any sort of detail, but nevertheless, I hope to give some kind of impression of what it's about. So you see the outline there, and now the page down doesn't work. I don't know why. So I'll have to do it this way. So the Pirogov-Sinai theory is a generalization of the Peierls argument, which I assume many of you know about. Nevertheless, I'll start by recalling how that works. And a significant element of Peierls' argument is the the spin flip symmetry. And well, the main purpose of the Pirogov-Sinai theory is to discuss models, so they're classical spin models where there is no such symmetry. And so the typical example of such a model is the Potts model, and so I'll introduce that next. And then instead of doing straight away Pirogov-Sinai theory, I'll discuss an example of this Potts model, the inhomogeneous example with Q equals 3, a rather special example, and do an approximate analysis of that. And at least that should give you some insight into what the situation is if there is no such spin flip symmetry. And then I'll discuss a little bit Pirogov-Sinai theory, and at least give you an outline of how the proof goes, but I can't give any details there. That's just way too technical. And a crucial element of Pirogov-Sinai theory is the introduction of so-called contour models, and I'll at least tell you what they are. So let me start with the Peierls argument. So the Peierls argument is the argument to show that there is a spontaneous magnetization in the Ising model in dimensions d greater or equal to 2, of course. So I'll recall the Ising Hamiltonian there. So it is a model on a lattice z to the d arbitrary dimension, and for a finite subpart of that lattice lambda, we look at the spin configurations, that is spins which have values plus or minus 1, and the collection of such spin configurations we denote S lambda there. And then the Hamiltonian, that is the energy, is minus J, and I introduce a minus in order to get ferromagnetism, and then a sum over nearest neighbors, x, y, inside lambda, of the product of the spins. And I also introduce a magnetic field H there, and again with a minus sign, which indicates that if H is positive, then it favors, that is, the energy is lower when the spins are up in the same direction as the magnetic field. Now, given this Hamiltonian, the Gibbs measure, that is the probability distribution of spin configurations, is given by mu lambda beta there, which is 1 over a normalization constant called the partition function times the sum over all possible configurations in a given set A of e to the minus beta h lambda, where beta is the inverse temperature. Well, I guess you've seen this before. So now what Peierls showed is that if, well, in fact, his proof is rather sketchy, but nevertheless, he showed that in dimension d greater or equal to, there is spontaneous magnetization. And what does that mean? That means that if beta is large enough, that is the temperature low enough, then the Gibbs measure at infinity at inverse temperature beta with plus or minus boundary conditions gives you a magnetization, that is the expected value of S0 is plus or minus M0, where M0 is strictly positive. Now these measures mu plus minus beta are the thermodynamic limits of the measures that I introduced on the previous slide, that is mu lambda, where lambda tends to the whole lattice. And one can show that such limits always exist. And so with plus minus boundary conditions, you then get a spontaneous magnetization. And that also means that there is a phase transition, because those two measures then cannot be the same. Note that Peierls does not show that these measures mu beta are actually pure states, that is pure phases of the model, whereas Pirogov-Sinai theory does show that as well. So it is, even for the Ising model, slightly more general than this. Now the proof of this statement in Peierls' case depends on rewriting the Ising model in terms of contours. So let me make a picture. So this picture has red and blue sides, and red stands for an up spin, plus spin, and a blue side for a minus spin. And you see that I have taken positive boundary conditions. So around the boundary, it's all red. And then you see some islands with blue spins. And I'm assuming here that the temperature is already fairly low, so that in majority there will be plus spins, but in fact that is what we want to show. Now, you can see that instead of the configuration of spins, you can also give a configuration of so-called contours, that is closed boundaries between plus and minus spins. So the black lines denote when spin on opposite sides of it are different. And once you know the boundary condition here, plus, then you can reconstruct the whole configuration by simply knowing what these contours are. So the closed circuits are all separate contours, and the collection of such contours is called the boundary of the configuration. And then Peierls' argument consists of two parts, namely an energy estimate and an entropy bound. And so it's also called an energy entropy argument. Now the energy estimate gives you a bound on the likelihood of a contour, any given contour, and then the entropy bound gives a bound on the number of possible contours. So let me specify that. I wrote again the measure now, but with h equals 0. So here we can assume that h is 0 because of symmetry of the model. It is clear that the phase transition, if it exists, will exist at h equals 0. And this is a rather important remark, which I'll come back to. And so we take positive boundary conditions, which here is indicated by taking also pairs which intersect the boundary of lambda, and then outside lambda it's +1. So Sx is +1 if x is not in lambda. And so this gives measures on lambda with positive boundary conditions. And if you look at those measures now, then the first statement is a statement on the likelihood of a contour. So you fix a given contour, so some closed circuit of lines, or in 3 dimensions, for example, they are plaquettes. So they're little squares, again, between 2 spins. And then what this bound says is that the probability, so the mu lambda plus gives you the probability with plus boundary conditions that gamma is one contour for the configuration S lambda. And the probability that this happens is less than an exponential factor depending on the length of the contour, or if you are in 3 dimensions, the area of the contour. Now, how do you prove this? This is not difficult to prove, so I'll do that on the next slide. So if this ds lambda, that is the collection of all contours, and then between absolute values is the sum of the lengths of the contours, or if you like, in 3 dimensions, they are the areas of the contours, the total area of the contours, then you can write this measure, so this mu lambda plus that I had in the previous slide, you can write it as a sum over S lambdas, which, so they're configurations which contain gamma as one of its contours, divided by the sum over all S lambdas, and then the exponential factor, the Boltzmann factor, e to the -2 beta j times the length of the contour. Notice that there's a factor 2 because if you have a contour, then that means that the spin flips from plus to minus, and therefore the energy flips by 2 times j. And beta, of course, is the factor. Now notice that I've left out a factor corresponding to all the equal sites, but that cancels from the top and the bottom of this quotient. And so you get it completely in terms of the total length of all contours in the configuration. Now then you introduce omega gamma lambda, the set of configurations S lambda for which contain gamma, so that has an index gamma. And one introduces a bijective map, that is a map between omega gamma and the complement by simply flipping all spins inside gamma. So let me show that here up above. So for example, in this bottom contour there, so there's 3 contours here, an outer one, then an inner one, and a tiny little one inside again. If I flip all the spins inside the outer contour, then the blues become red, the red becomes blue, and the blue becomes red again. And you see that then the outer contour disappears, but the other contours are still there, even though they are now an opposite sign. And so this happens in general. And so what happens then is if you flip all spins inside a contour, then that contour disappears from the configuration, but for the rest, all the contours remain. And that means that if you have an S lambda which has that contour, then the total length of the contours reduces precisely by the length of the contour that you flipped away. And that means that the probability that gamma is a contour in S lambda in this expression 5 you get a factor e to the minus 2 beta j gamma, that is just this gamma here, which drops out of the sum, and then the sum is over S lambdas which do not contain gamma. But of course, this numerator is still smaller than the denominator, and that gives you the bound that I said holds. Notice that in this argument is very crucial, this spin flip invariance, and that is what we want to get rid of in the future. So in the Peierls argument, the spin flip symmetry is a crucial element. Now then there is a second part to the argument, and that is to count possible contours. And that's the lemma 2. It says that if you count all closed contours gamma of length or area, depending on the dimension n, which surround the point 0 in ZD, then that is bounded by n times 3 to the n. And this is easy to see because if you start at any given little line of the contour, then that line cannot be more than n removed from 0, so at most at distance n, along the x1 axis, say. And so if you then start with that one, and then continue adding little plaquettes or lines onto it, then for each one, you have only 3 possibilities, namely up, left, or right, if the first plaquette or the first line is facing up. And then, so every time you add one, you have 3 choices. And you might think that this is a bigger number for higher dimensions, but that's not so. If you look at a plaquette in 3 dimensions, then still to fit one onto it above or below, you still have only 3 possibilities. So you see this bound holds in any dimension, well, not 1. So this also means that the transition, the phase transition will occur roughly in the same point for all dimensions. Well, of course, this bound will not depend actually on the dimension. So then the rest is just a matter of putting these 2 things together. And so Peierls' theorem then says that there exists a beta 0, which is independent of lambda. So now you can take lambda to infinity or to ZD, and there's still such a constant M0 beta, which is the magnetization. And you do that quite simply by arguing that if the central spin S0 is -1, then there must be at least one contour which surrounds it, because we have plus boundary conditions. And therefore, the probability that it's -1 is less than a sum over possible contours. Well, the smallest contour you can have, of course, is 2D, that is right around the 0.0 or higher, and then Cn times the factor that I have in lemma 1. And now you see that since Cn goes like 3 to the n, if 2 beta j is greater than log 3, then this will tend to 0 as beta tends to infinity. And so that proves that this factor here is in fact even arbitrarily small, not just smaller than this, but even arbitrarily small if beta becomes large. So this is the Peierls argument. And now I want to introduce a more general model and see what happens then. So the more general model I'll consider is the inhomogeneous Potts model. So in the inhomogeneous Potts model, the Hamiltonian is replaced by this expression 8. And I denote it by h hat because I also need h without magnetic fields. Now, notice that now the spin values are more than 2. So I'll just I'll just label them 1 to Q, just like in the usual Potts model. And then we need to introduce magnetic fields in general for each one of the possible values of this Sx. So I introduce magnetic fields HR for each R between 1 and Q. And the interaction Hamiltonian, that's the H without hat, is given by this expression. It's a sum over potential values, and where the potential in the case of the Ising model, the potential interaction was just the product of Sx and Sy. Here we introduce an interaction between Sx, the spin Sx and Sy by the following expression. So it is a coupling constant J R prime, where R is not R prime, R is less than R prime, and then delta Sx R, so that's if Sx is R and Sy is R prime. So if Sx and Sy are not the same, then we get an interaction constant. And it is inhomogeneous, so this interaction constant now depends on which R and R prime we have. And that's the inhomogeneity, which makes the whole thing no longer symmetric. We will assume again that the J's are positive, and that discourages the Sx and Sy to be different. Now the ground state, so now we're going to first look at ground states. And in general, a ground state is defined as a minimizer of the specific energy. So that's the energy per site. And for the moment, I'm looking at the case where the H's are all 0. So that's this expression. So that's just for a given site. And then you look at only at neighbors. So here there were also, again, it was a nearest neighbor model. In fact, the Pirogov-Sinai theory holds for more long-range models as well, but really the essence of it is perfectly well explained by nearest neighbor case. So if the J's are all positive, like I said, then the ground states are precisely given by the constant configurations in this case, because in that case, S0 and Sx are never unequal. And so this is then 0, whereas if one has one pair which is not equal, then this would give you a positive contribution. So the lowest energy is attained when all spins are the same and irrespective of which R they are. And so there are precisely Q ground state configurations for this Hamiltonian, as long as the magnetic field is 0. Now, if the magnetic fields are not 0, if some of these magnetic fields are actually not 0, then some of those states will be favored or disfavored, and therefore there will be fewer ground states. And the number of ground states can be counted then as follows. So we look at the maximum magnetic field, and of course, the bigger the magnetic field, because I introduced a minus sign again, the bigger the magnetic field, the lower the energy, so that favors that particular R. And so if we introduce TR, that's the difference between H max and HR, then those HRs for which H max minus HR, that is TR, is 0, will give you still ground states, whereas those for which HR is less will no longer be ground states. And so this would give you a mapping actually from the magnetic fields to these parameters T, and those parameters T will all be either 0 or positive. So the minimum of the T's is 0, and so there's a map between the magnetic fields and OQ. Now I write here, in fact, the difference of the magnetic fields H2 minus H1 up to HQ minus H1, because of course, if you add a constant to all the magnetic fields, then that just shifts the Hamiltonian, but it doesn't change any of the relationship between the different ground states, nor in fact between the different thermodynamic states. And so Pirogov and Sinai, now the essence of Pirogov-Sinai is to show that this map is continuously deformed for low temperatures. And now I'll show you a little bit how that works, first by in an approximation. So this,
sorry, Tony, I missed what the B's are.
So they're the T's. So the T1
Oh,
to
you just
is the B's, yeah. But in general,
you're just renaming them.
In general, we will call them B. But here they're T's, yeah. So the T's are all positive or zero, and when they're zero, they are ground states. So now I'm going to consider a special case. I'll look at the three-state inhomogeneous Potts model, so with Q equals 3, and I'll first start with taking all the HR 0, H1 to H3 are all 0. And moreover, for simplicity, I'll look at this case where the interaction between 1 and 2 is J, and the interaction between 1 and 3 and 2 and 3 are both equal and larger, given by constant J tilde. So then we have two coupling constants, J and J tilde. And now what I'll claim is that the states S1 and S2, well, they are obviously equivalent because the energy between 1 and 3 and 2 and 3 is the same. So they must be equivalent. Those states are equivalent, and I'll show that, well, so I'll show only in approximation that for non-zero below temperatures, these states, the 1 and 2, are favored over the state S equal 3. So that means that for low temperatures, the free energy for the states S and 1 will be lower than the free energy for the state S equal 3. Now, of course, 1 and 2 are equivalent, so I'll just look at 1 and then later at S equals 3 as boundary condition. So consider the case where S equals 1. Now we're going to assume that we're at low temperature and that the actual states at low temperature but not ground states are just a perturbation of the ground state. That is, they are all S equals 1 except for some sites where it's 2 or 3. So that, of course, is a rough approximation because in general you will have more general contours. But let's consider only the case where there are individual sites where the spin is not 1. And then we can count, then we can look at the entropy for this. That is, we count the number of possibilities. And now let N2 be the number of sites where the spin is 2, and N3 the sites where it's 3, and N the total number of sites. Then the number of possibilities of choosing where these 2s and 3s are is given, of course, by this binomial factor or trinomial factor. And then the entropy is given by 1 over n times its logarithm. Well, I hope you're familiar with this kind of counting. And now if you take, so rho 2 is then the density of such 2 sites. So that's n2 divided by n, and rho 3 is n3 divided by n, and then this is the remaining sites. Now we're going to assume that rho 2 and rho 3 are much less than 1, so n minus n2 minus n3 is roughly n. But anyway, if you take the limit of this expression, then you get, well, I didn't introduce a KB, but it's minus rho 2 log rho 2 minus rho 3 log rho 3 minus, and so that's just the 3 factors that you get from there. And this calculation is quite simple by using Stirling's formula. And now I'm going to assume that rho 2 and rho 3 are much less than 1. And then log of 1 minus rho 2 minus rho 3 is approximately minus rho 2 minus rho 3. And so I then remove this second order term, and what I get is 2 separate entropies, namely minus rho 2 log rho 2 minus 1 and minus rho 3 minus times log rho 3 minus 1. So this then is the entropy. And so the free energy or free energy density here is given by the energy minus the temperature times the entropy. Now the energy is very easy because they're single sites. So the change in energy due to a site with spin, or S spin equal 2, is exactly given by this interaction constant between 1 and 2, which is J, and then 2D is the number of lines or plaquettes bordering that site. And similarly, for the 3 sites, we get J tilde because the interaction constant between 1 and 3 is J tilde. So this is the free energy for arbitrary possible densities rho 2 and rho 3. And now we need to minimize over the optimal situation. So we minimize over rho 2 and rho 3. That gives you these rho 2 and rho 3. And from that, you will see immediately that if beta is large, so at low temperature, then my assumption was right, that rho 2 and rho 3 are indeed much less than 1. So for large beta, we find that the minimum free energy at boundary condition 1 is given by minus, so if you insert this here, then you get minus 1 over beta times e to the minus 2 beta dj plus e to the minus 2 beta dj tilde. So you have to remember that expression, because now I'm going to do the same calculation for the boundary condition 3. So let's consider now the boundary condition S equals 3. Now in that case, one has some sites where S is 1 or 2. So impurities Sx equal 1 or 2. Now 1 and 2 are equivalent, so I can count simply, I can just look at the density of sites rho of total impurities, the total density of impurities rho, and then I get the usual icing entropy S rho. But in addition, I can choose then at each site whether I have a 1 or a 2, and that gives rise to an additional constant rho log 2. And so in this case, we get that F3 with boundary condition 3 is given by 2D rho J tilde, because the coupling constant between 3 and 1 and 3 and 2 is both J tilde, and then minus this entropy. And when we minimize, we get F3 minimal is minus 2 over beta e to the minus 2D beta J tilde. And if you remember now, the other one with F1 was 1 over beta e to the minus 2d bj tilde plus e to the minus 2d beta j, and j is less than j tilde, so e to the minus j tilde is less than e to the minus j, and therefore with a minus sign, F3 will be bigger than F1. So this shows you that if the external fields, the magnetic fields are 0, then F1 is lower than F3, and therefore the equilibrium state will be S equals 1, or of course 2, because 2 is equivalent to 1. So one finds then that there is coexistence of phases 1 and 2, but not 3. Now, of course, what can we make S3 to be also in, oh no, something happened. How do I get rid of this? Can we make the third state also to be in equilibrium? Yes, if we introduce a field H3 positive. Now then you can do this calculation again, now but in the presence of a magnetic field H3 in the 3 direction. You get slightly more complicated expressions, but essentially what you find is that H3, if you ignore now the denominator, then H3 is just the difference in the free energies that you need in order to get also coexistence with the third phase. So by introducing a magnetic field, one can make all three phases coexisting. And so one then gets a triple point. And the crucial thing to realize here is that you need this magnetic field H3 here. Now, of course, we can also keep H3 equals 0, and then what it means, the previous conclusion really, is that the 3 is not actually a proper phase. So what happens then if I nevertheless take boundary conditions which are 3? Well, what happens then is that, in fact, what I said would be true, that there are only individual sites equal 1 or 2, is not true. What happens then is that one gets a large contour gamma along the boundary of lambda, and then inside that contour one gets either 1 or 2. So this large contour will have a length which is given by the boundary of lambda, and therefore an energy which is 2d j tilde, where j tilde is the interaction between 3 and one of the others. And because the boundary of lambda is much less than lambda, this is negligible in the limit, and so it is then advantageous to have such a large contour, making the state back into a 1 or a 2. Now, to get the complete phase diagram, we also need to look at the case H2 non-zero. So we've looked already at the case H3 non-zero, but we also need to case H2 non-zero. And in fact, H1 we don't need to look at, because I already pointed out that you can always take H1 equals 0, because adding a constant to the Hamiltonian does nothing. Now, by the above analysis, we have seen that if H2 is 0, then there is a critical value of H3, H3c, given by roughly the right-hand side of 16, such that if H3 is less than that, then the states 1 and 2 coexist, whereas if H3 is bigger than that value, of course, there's only the third phase. Then we have such a large magnetic field that it dominates the others. Now, you can do a similar calculation now in the presence of H2, and one finds that the states 1 and 3 coexist if this holds. So if H3 is the critical value plus some factor times H2. Now, in this case, you need H2 negative, and then 1 and 3 will coexist, but not H2. And similarly, you can make 2 and 3 coexist if H3 is again the critical value plus H2 minus some factor times H2. Now, these are still straight lines, and they emanate from the triple point. So the phase diagram looks like this. Well, so approximately the very low temperature. So we have here this point elevated above the axis. That is the critical value H3. And then there is a line going to the right up where H2 and H3 are equal, but not quite. It's given by this equation here. H3 is H3 critical plus this factor times H2. And there, the 3 and the 2 coexist. And similarly here, we've already seen that along this line here down below the y-axis, 1 and 2 coexist. And then there's this line here where 1 and 3 coexist. And notice that this phase diagram is a slight perturbation of the ground state phase diagram. In the ground state, we had these same lines so along this dotted line, diagonal dotted line, H2 and H3 are equal, but they are positive, whereas H1 then is 0, and that means that 2 and 3 coexist. So the line has just been slightly tilted, and similarly, this point, the critical H, has just moved up slightly, and the line is slightly tilted as well. So this is a slight perturbation of the phase diagram at zero temperature. And so the essence of Peierls' Pirogov-Sinai theory is that in fact one can prove that this holds for low temperature, not just approximately, but exactly. And of course, the problem then is to find these critical fields H3. So these lines now will not be straight lines anymore. They will be slightly curved. And the question is, how do you find those curves? And that's the main exercise of Pirogov-Sinai theory. Now, the first thing they did was to generalize the concept of contour, because now there are 3 or more colors or spin values involved. And so it's not so clear how to distinguish those different phases. And so they introduced a new type of contour. And so first of all, the boundary, which will consist of contours as before. So one takes 2 by 2 or 2 by 2 by 2, 2 to the d cubes. So 2 sides by 2 sides. And then one takes a union of all those cubes where the configuration is not constant. Now note that these cubes, the x goes over zd. So in general, these cubes overlap. If you change x by 1, then the cube moves 1 to the right, but it's 2 by 2, so it's still overlapping. And a contour, of course, is then again defined as a connected part of this boundary. Now, in fact, you need to also take into account the particular configuration on the contour. And so the contour is defined actually as a pair where gamma is some connected set, in fact, a subset of the boundary of S, and S gamma is the configuration as restricted to gamma. Now, so this is a little bit more complicated concept, so I'll illustrate it here. So here's a Potts configuration with Q equals 3. So the three spin values are denoted by colors green, blue, and purple. And you see the boundary conditions here are green. And now what are a contour? Well, first look at a single side. So you see, if you take a 2 by 2 square, which contains this single side, then it is green in some places and blue in one. So it's not constant configuration. So that's part of the contour then. And so you get a 3 by 3, and in 3 dimensions of 3 by 3 by 3, if there's a single side. If you have more sides, then you have to look at all 2 by 2 squares which overlap with, so where the configuration is not constant. So for example, this square here, is the configuration is not constant. In fact, if you look closely, then I made a mistake in this graphic, which I have corrected in the next one. So here, this is the same configuration, but only the contours indicated. So the contours are these connected sets, and here another one, and this one, and 3 more there. And you see that once you know the contours plus the configuration on it, so you also need the configuration on this contour, then you can complete the configuration of spins by just extending. So here, all this in between will be green, and inside here will be blue, here inside will be blue, and here inside will be green. So you can, once you know the contours, including the spins on the contour, then that'll be sufficient to recover the spin configuration. Notice also that you do need to know also the spins on the contour, because for example, this purple bit here, if there was a fourth color, it could be, for example, also brown, And if you replace the purple by brown, you get exactly the same contour, but with different configuration. So the configuration is important. Now, here's the statement that I already said in words. So Pirogov-Sinai theory proves the following theorem. So if beta is large enough, that is low temperature, there is a neighborhood of 0 that is in r to the q minus 1. So these are the differences in, so this is hr minus h1 from r is 1 to q, or r is 2 to q. And there's a homeomorphism. So for small differences in magnetic field, there exists a homeomorphism. So continuous map from this neighborhood to a neighborhood of the set that I introduced already, where the minimum Bm is 0. So they're all positive, and so they're part of a quadrant. So if you look at 3 dimensions, so then it's all the sides, the positive sides of the so between 2 axes. And then if the values where B is 0 are M1 to Mn, then so these are the spin values for which H is 0, then there exists n translation-invariant limit Gibbs measures representing distinct coexisting phases. So that means that if n, capital N of the B's are 0, so you see that there's at least one 0 because the minimum is 0. But if there are, for example, 2 equal to 0, then there are 2 and precisely 2 coexisting phases. Now, in fact, what I said before is that what's in Sinai's book is not complete, because all he shows is that there are at least n such phases, and the proper statement is that there are exactly so many. Now, how do they prove this? They prove this by introducing a concept called the contour model. And then they show that there is a map between each phase of the model, of the spin model, and a particular contour model. So for each phase, they introduce contour models. And what is a contour model? A contour model is kind of an abstraction. So it's given by some functional, so that's a kind of an energy functional on a set of contours, which are now abstract things. These contours are still connected subsets of ZD with some arbitrary decoration, and in our case, those will be spin values inside the contour, but they have to be consistent. That is to say, you see that when you have a contour here, then the outer edge of the contour is all uniformly the same color. And that is always the case. And similarly, the inner edge, the blue bit here, is also all the same color. And that is necessarily the case by the definition. So one would have to have a consistency condition about this decoration, but we don't worry too much about that in terms of an abstract contour model. And in our case, those connected sets will be cubes of psi 2. Now, the function f can also depend on the decoration, and in fact, they are not very clear about that in the beginning. Now, we'll assume only 2 things about f, namely that it's translation invariant and satisfies the Peierls condition, as they call it, and that is that there is a constant tau, positive, such that for every element of every contour, gamma, the energy of the contour is at least tau times the length of gamma. And remember that in Peierls' argument, this was crucial for the energy estimate, because if the energy is big enough, then the existence of large contours will be suppressed, will be very unlikely.
Sorry, Tony, can you repeat what you meant by a decoration again? Just
that doesn't matter. It's any so apart from the subset, you can have some spin values on it. And here it's not specified what they are because the only condition that matters is here and there's no such decoration involved.
Okay, so it doesn't refer to some sort of inhomogeneous, it refers to some additional spins on the contour.
It refers to some additional coordinates which you don't, spin coordinates, which you don't specify. But in our case, there will be the spins, the spin values on the set gamma. So now the idea is that the distribution of external contours of the spin model only correspond to that of a given contour model, and the contour model will correspond to the outer boundary condition of those external contours. Now note that all external contours, if I go back to the contours here, all the external contours will have, now here we have no internal contours in fact, so all the external contours all have green external boundary. But that is necessary. Once you specify an outer boundary condition, then it's necessarily the case that they all have that same outer boundary condition as long as they're in external contours. There can be a contour, say in here, there's a space here, and that space, of course, is quite small here, but it could be bigger. And so there could be another contour in there, and that contour would then have outer boundary condition blue. But once we have chosen a boundary condition, then it must be all the same. The external contours all have the same boundary condition. And so we then make a correspondence between such spin contours and a contour model, so a functional f on those contours, only the external contours. Now note, as I already remarked, the inner region of a given external contour is also, we can put another contour in that, so we can consider that again as a separate region lambda where we can insert more contours. And so we can then consider this inner region in itself also as a starter region with a given boundary condition. And so we then get a mapping between the spin model, the external contours of the spin model on lambda with, say, blue boundary conditions with another contour model. So in that way, we get contour models for each of the boundary conditions, and they kind of, so they're inside one another. And every time that you introduce more contours inside another one, the F's, so the corresponding energy functionals F for the contour model will change. But if the likelihood is smaller and smaller, these F's will be changing less and less. So this is the idea. And so there will be a fixed point once you have introduced all possible contours inside and inside one another. There will be a fixed point of this map, and that fixed point determines not only the energy functions for each external boundary condition, but also the critical value of the fields HR. So this is the idea. By just moving, putting contours, inside contours, etc., one gets a better and better approximation of the actual spin model that you have, that you started with. Now I'll write down here what a contour model is. So one introduces a partition function for the contour model, very similar to the Ising model, remember. So this should be D contained in C. So D is a collection of contours. And then we write, just as before, we write the total energy corresponding to each contour, and we take the Boltzmann factor and the sum over all possible configurations, but now contour configurations. Now, in fact, one needs a slightly more general thing, namely a parametric model, and that's a model where, apart from this factor f of gamma, one introduces another constant b, a positive constant, and that B is related to the B's that we had before. So there will be a B for each R, and there will be an F for each R. But an individual contour model, you don't need to introduce the R's. And then this B is a positive constant, and it multiplies the size of the interior of gamma. So that's what they do. And so that's like a magnetic field, because the gamma is going to be something quite thin, even though on my pictures it didn't look like it. They will be thin, and the interior of gamma will be in general a fairly large region. So this is proportional to the size of the volume, whereas F is considered proportional to the area of the contour, but that's meant to be like very thin.
Sorry, and you have restricted here to homogeneous model. Because you're taking
translation invariant. It's translation invariant, but it's not homogeneous.
It's not isotropic, I suppose, is what you mean, is it?
No, so the different spin, so this doesn't, there's no spin here yet. This is an abstract contour model. But when we introduce spin values, they give, you get an FR, and the FR depends then on R. And so you get a F1 to FQ, and so the vector functional F1 to FQ corresponds to the spin model.
Oh, I see. It's in internal space, in spin space. You're not.
No, so this is abstract contour model, and it.
Yes, I understand that. Yeah, but the homogeneity in space or translation invariance is guaranteeing that you have the volume of the interior of the contour.
Yes. So
your more general case will be.
That's what I'm going to say here now. So how does the proof now work? Well, I can indicate a little bit the steps. So steps 1 to 4 all concern just a single contour model. So one first has to know details about the contour model. And the first thing to know is that the thermodynamic limit of a contour model exists. And this is done using a kind of Meyer expansion. And the idea is that if tau is large, then contours are rare. And if contours are rare, you can consider them as kind of particles, as a gas of particles. And so then one can apply a Meyer type expansion for the gas of contours. Well, so that's all I can say. If you've seen Meyer expansion for a classical gas before, it's somewhat similar to that. In fact, it's slightly easier, but nevertheless tricky. So one has to prove then that this Meyer expansion converges. And once you have that, then you also get number 3, then the correlations, the correlations decay exponentially. And then one also needs, as I said before, the distribution of the external boundaries. So again, in a contour model, you can have contours inside contours, etc. And so one then looks not just at the distribution of all contours, but also especially of the external boundaries, because this distribution we want to relate to those of the spin model. And then one proves that the pressure, so a kind of pressure also exists for such contour models. And like you already indicated, for that one needs translation invariance in order to, well, glue together different regions. And then the next step is, like I indicated, a mapping between the spin model with a given boundary condition and the distribution of external boundaries for a contour model. And then one needs, so that gives you then certain F1 to FQ functionals, contour model functionals, F1 to FQ. And then by introducing contours inside contours, you get a mapping between these Fs. So a mapping from one set of Fs to a new set of Fs as you introduce more and more contours. So contours within contours. And then you have to show that this mapping converges to a fixed point. And once you have that, you can look at the value of the pressure of the contour F, of the contour model corresponding to R, plus beta times the magnetic field. And the maximum of that expression then, if that is less than the maximum of that expression, then it will not be in coexistence with the phase where this maximum is attained. And so the phases where this maximum, or the M's where this maximum is attained, will then be the coexisting phases. So that's the idea. And again, one has to show that in the case where it is strictly less, that then there exists, as in this picture, there exists such a large contour such that inside that the configuration, the spin configuration, flips to one of the boundary conditions which are in equilibrium or in coexistence with the maximum, for which it is maximal. Now, in fact, that is one of the difficulties. So Sinai, in his book, actually leaves out this argument, and he only shows that there exist at least so many phases, but he doesn't show that any other phase for which this is less. In fact, it is not in equilibrium. And that is quite a long argument. And I'll now indicate a little bit of the idea of that. Now, this is my last slide. So in order to show the existence of a fixed point, we want to show that in some sense these functionals F converge, and in order to give a meaning to this convergence, we need a norm. Now, the norm on the space of functionals, the natural norm would be a supremum over all possible contours gamma, and then the size of F gamma divided by the size of gamma. Remember that the Peierls condition was that F gamma is greater than some factor times gamma, the size of gamma. But it is natural to assume that F gamma will be of order of gamma, so it will also be less than some multiple of gamma, even though a bigger multiple. And that is the natural norm of F, but in fact, Pirogov and Sinai use a much weaker norm, which I will not write explicitly, it's a bit complicated, but it's a kind of weak norm. And now I'll indicate how that works with a very simple and trivial example, which you will find too easy, but nevertheless, it gives you an idea. So suppose I have a map from the space L201 to space L201, and it's given by the following. AF, so F is an L2 function at a point x in 0, 1, is root 2 f2x if x is less than a half and 0 otherwise. So what this map does is squeezes the function to the left, but it also increases its height. And now it's easy to see, because I chose this square root 2, that the 2 norm of AF is precisely the 2 norm of F. And so from that, you cannot conclude that it converges. And so we would like to show that there is a unique fixed point of the map A, and from this you cannot do that. And to do that, we introduce a weaker norm, namely the L1 norm. So L2 is contained in L1, and now it's easy to see, because of the root 2, the absolute value there integrated needs a factor 2, so that gives you a spare 1 over root 2. So the 1 norm of AF is 1 over root 2 norm, 1 norm of F. So on the L1 functions, A is in fact a contraction, and so it converges, and that means that there is a unique fixed point, namely 0, which of course you had long seen, but nevertheless that's a trivial example. I mean, you can easily make this example more complicated so that you don't see so easily what the fixed point is. But this, now the 0 is obviously an element of L2 as well, and so it is the unique fixed point of A also in L2. And so this argument by Pirogov and Sinai works the same way. You introduce a weaker norm, and then you show that with respect to this weaker norm, it is in fact a contraction, and therefore there exists a unique fixed point. Now, what they leave out is to show that this fixed point is in fact also in the space given by the norm 22. Now, in their case, this is not so important, because for the existence or the coexistence of phases, you only need to show that Pirogov condition holds, Peierls condition holds, and Peierls condition, of course, is the opposite bound. So then you don't mind if f is large. But in order to show that there exists such an external large contour, you need the opposite, because you need to show that this large contour does not contribute more energy than corresponding to the size of the contour. If this f gamma is much larger than gamma, then it could be that this contour is not favorable at all. So to prove that there exists no more boundary conditions for which they coexist, one needs this large contour, for which one needs that 22 is in fact finite. And so one does need to prove that after showing that there is a fixed point, that this fixed point is in fact also in the smaller space given by this norm. Now, so in my forthcoming Dias communications, you can read how all this is done and many of the details, but I hope I've given you some idea at least of how this whole theory is put together. Thank you.
Thank you very much, Tony. The floor is open to questions. Does anyone want to begin? I'm not quite sure where to begin. You've given us a lot of material, Tony, for those of us that aren't familiar with the technical details. That's okay. One of the things that strikes me is how easy is it to prove that a given model has a contour representation, because that seems crucial.
Yes, that's crucial, and so the map between the spin model, the external contours of a spin model, and the external boundaries of a contour model is in fact not so complicated. I could have written that down, but it just is an identification of this partition function and the corresponding partition function of the Potts model. So that's just putting this psi equal to z.
I mean, I can see it in certain ones like the Potts model and ones like that, but in general, it isn't obvious to me that I will be able to find a.
So in general, the general case is, the Potts model is pretty general. I mean, there's not much more you can do other than introducing longer range interactions. So you could have interactions between spins which are not neighbors. And then all you have to do is introduce larger squares. So instead of a 2 by 2, so the contour collection is a union of 2 by 2 squares or cubes. And if you have a larger range, then you need to correspondingly also increase the range of the contours. So the contours will be, of size proportional, or as thickness proportional to the range of the potential.
But I think you also need that that the phase that you have first order boundaries between the phases.
I don't
Looks
know
to
what
me
you mean
like,
by first order boundaries.
I mean that you don't have a continuous transition with
Yeah, so there, you know, this only applies to so the whole Pirogov-Sinai theory applies to discrete spin models. So
well, if I remember correctly, the Q state
the
Potts
classical
model.
spins are you know, only from 1 up to Q. So
Yeah,
that's
but I think for the 10 state Potts model, it becomes very weakly first order. And
well,
some higher ones have a second order transition or a continuous transition.
yeah, the transition here is only considered for very low temperature. So
Okay,
what happens at higher temperature, that doesn't say anything about.
Okay. And the other question is, I remember these arguments of I think it was de Bruijn,
Yeah.
which seems very close to the same thing as Pirogov-Sinai, but not in contour language. Are they? Am I misremembering?
Well, I don't quite know. I mean, de Bruijn has done a lot of work.
I was thinking about the de Bruijn boundary condition for trying to and making some argument.
Well, so there's an interesting point. So the de Bruijn boundary condition for the Ising model, he shows that in 3 dimensions there is a
roughening transition. Yeah,
there is a non-translation invariant equilibrium state. That's
exactly
what he shows, and you just split up the lattice in a top and a bottom half, and you put plus boundary conditions top, minus boundary conditions at the bottom.
Yes.
In 2 dimensions, the dividing line between them becomes so wiggly that there is no other phase. But in 3 dimensions, it becomes kind of rigid, and so there is then a separate phase which is not translation invariant. In 3 dimensions, you have equilibrium states which are not translation invariant.
Exactly, you get an interface between them, and with a roughening transition.
And of course, this is this is not considered here at all. This is only considering translation invariant boundary, translation invariant states. Now you can introduce non-translation invariant boundary conditions, and there's a theory by Galavotti and Miracle, which shows that at low temperatures there is still only the translation invariant. So even if you introduce a non homogeneous boundary condition, it still becomes the translation invariant. Sorry, that's not true. But the translation invariant states are still the same.
Okay. Yeah.
So you can. But so this whole theory only looks at translation invariant states. It doesn't look at so they are called pure phases. So the phase diagram is just a phase diagram for pure phases. So it's a coexistence of pure phases.
Yes. Okay. Are there other questions?
Can I ask a question?
Please, Bob.
It's very naive, but by the way, the material was very difficult material presented very cogently. I think quite good.
Thanks.
The final, it looks to me very technically difficult, but the last statement that the final result depends on the norm.
Yeah.
Can one check it experimentally?
Oh. Well, you see, so to be honest, I'm not entirely happy with this theory, because I would have hoped that one would be able to get only a mapping between the magnetic fields, whereas they introduced these general, functionals F, and so you have a space, an infinite dimensional space on which you need to do this convergence, which makes it so complicated. And one expects, of course, that the energy of these contours is simply given by the Hamiltonian itself, the spin Hamiltonian. So for me, it's a little bit unsatisfactory that one has to introduce all these functionals f. But you know, so far I have nothing better. So
didn't Bogoliubov have some alternative approach to proving some of these type of results?
No, I don't think so. No.
This vague recollection of Bogoliubov quasi-averages or something like that.
Oh no, that's a quantum thing. Yeah, but that concerns mean field quantum systems. So that is quite far removed from this. No, see, so these are nearest neighbor or, you know, short range interaction models.
Okay.
Which are much more realistic, but also more difficult to treat.
Okay. Are there other questions? If not, I will stop the recording and we can continue.